And we're going to show you something that's going to be really useful to you, and you're going to get the first glimpse of what your test is really going to look like, okay? And so before we're still kind of in this whole rational roots theorem thing. One of the people who helped develop that was a man by the name of Descartes. He put together what is referred to as the Cartesian plane, your XY coordinate axis, which really changed and revolutionized mathematics. And he said that you can actually anticipate how many different solutions there are that are positive and negative for a polynomial. So notice this says the number of positive real, and so it's referring to real numbers. So it could be, say, the number 5/3, which is rational, but it could also, say, be the number the square root of 2. It does not isolate it to just rational. It could be any real number. But the number of positive real solutions is equal to something. The number of negative real solutions is equal to something. So before I write it down, I just want to show you, here's an example of a polynomial that has positive and negative solutions. How many positive solutions does that polynomial have? How many times does that polynomial cross the x-axis on the right-hand side? Once. There's one positive real solution. How many does it have on the left-hand side?
3.
3. So it's a 4-3 polynomial, 3 that are negative and 1 that's positive. We can actually figure out ahead of time a little bit of how many of those that exist by looking at this. The number of sign changes in P of x or less by a factor of 2. Now this whole less by a factor of 2 thing, you're going to have to let me explain that to you in a second. But right now, I'm going to start by looking at this polynomial right here. And I am going to write down the number of positive real solutions that it has. Okay? In order to determine the number of positive real, I look at the number of sign changes in the polynomial. So is 3 positive or negative? Does it switch or stay the same? Switches. Does it switch or stay the same there?
Switch.
And then it switches again. How many changes were there? So that means that there's 3 real solutions that are positive. Okay? Now, you learned the other day that every once in a while, some polynomials don't have real solutions. They have imaginary solutions. And so I'm going to give you a little hint that guides you into actually our lesson that's going to be on Monday and Tuesday, is that if polynomials have imaginary solutions, they come in pairs. So there can never be just 1. There can never be 3. It's always got to be an even number. So the fact is that there might be 3, but if there are some imaginary solutions, they would come in a pair, so we subtract 2 off for that pair. So maybe there's just 1. So suppose that I would have listed 5 solutions. We would have said 5 or 3 or 1. Suppose we would have listed 6 solutions. We'd say 6 or 4 or 2 or 0. See what I'm saying? Everybody see that? Okay. So that's the number of positive real. Over here, I want you to look with your friend and decide how many sign changes there are in that situation, which would indicate the number of positive real. Take 10 seconds, talk to your friend, go.
Looks like 0 to me.
Get 0?
Yeah.
There are no sign changes. So there are no positive real solutions there. You would not ever want to try a positive number for the rational roots theorem for that. It won't work. There's no way that you get a positive solution. Let's talk about the number of negative reals. It's equal to the number of sign changes in P of negative x or less by a factor of negative 2. Okay? So it's the same statement from above. It's just instead of P of x, we're going to do P of negative x. So I can't look at my original polynomial. Instead, I have to look at P of negative x. So I'm going to take a negative x and plug it in for x here. If I take negative x and plug it in for x and cube it, am I going to get a positive 3x cubed or a negative 3x cubed? Negative 3x cubed. Will this stay a minus 4x squared or change to a positive 4x squared? Stays the same. Will this change to a negative 5x or stay a positive 5x? Negative 5x minus 2. Notice that if it's to an odd power, it's going to change, but if it's an even power, it's going to stay, right? Kind of practice that whole piece before. This is like the third time we plugged in a negative x. Now look at this. How many sign changes are there in that scenario? There's none. So the number of negative real, there's none. So as we look at the total real solutions, the total number of real solutions, we are going to combine these together, okay? 3 plus 0 is 3. 1 plus 0 is 1. There's either 3 real solutions or there's 1 real solution. That's what we know about this polynomial. You tell me, if we have 3 real solutions, how many imaginary would you then have? None. Why? It's to a degree of 3, so if 3 of them are real, you can't have any imaginary. Suppose there was 1 real solution, then how many imaginary would you have? You'd have 2. So you'd have 1 real and 2 imaginary. Everybody see that? Now, somebody said earlier, they're like, well, Mr. Gans, I don't get what you're saying, because you also said the other day that everything factors. It can't factor if you got imaginary solutions. They make a really good point, don't they? They make a really good point. Except they're lying, because x squared minus 1, does that factor to what? Yeah. And you can see that there's not any imaginary solutions there, are there? But suppose you have x squared plus 1. You say, well, that doesn't look like it factors, does it? It does. X minus I times x plus I. Even imaginary solutions factor. And that's what you'll see later on. Okay, move to this one, okay? We go p of negative x. Is this negative x to the fourth going to change or stay the same? So I got negative x to the fourth minus, is it going to be minus x squared or plus x squared? Another minus x squared and then minus 1. So how many sign changes are there? There's no sign changes. So how many total real solutions are there? There's none. You don't even need to bother with the rational roots theorem. There's no way that you're going to find those real solutions by using the rational roots theorem. If there are no real solutions, how many imaginary are there? There's 4. All of them are imaginary. We flip it over. We use Descartes' rule of signs all the time. Descartes also came up with an idea of saying, hey, how can we make better choices about what works and what doesn't? Remember yesterday how you were listing like negative 48, negative 24, negative 16. You're like listing all of those at like 2, 3, 4, 6, 8, 12. Remember how tedious that got? Like you're like, hey, please like isolate the actual ones that could work. Like, do I have to try all of them? And Descartes says, I got a great idea to show you how to kind of find the biggest one and the smallest one that could work. He calls it the upper and lower bounds theorem. And it works like this. Suppose you plug in a positive number into the synthetic division, okay? So we just plug in a positive number in our synthetic division up top. If your results that are produced down below are all non-negative, meaning they could be positive or 0, okay? Suppose your results come out like that so that there's no negatives. Then we know this. B is an upper bound. Meaning there are no solutions that are bigger than B. None. So we'll start out before we do the negative one. We'll say that show that the polynomial p of x is equal to that has zeros that lie between negative 3 and positive 2. If they lie between negative 3 and positive 2, which was the upper bound? 2. So this is the upper bound, okay? So we're going to take 2 And we're just going to run it through the synthetic division here of 1. Notice I don't have an x cubed, so it's a 0 for x cubed. Negative 3, positive 2, negative 5. As I run this through, 1, 2, 2, 4, 1, 2, 4, 8, 3. Hopefully you've gotten pretty quick with the synthetic division, have you? It's amazing how quick you can actually be with it, isn't it? What do you notice about all those numbers? They are all positive. Therefore, we know that 2 is an upper bound. I didn't know that Brecken liked John Denver. What'd you say is the good song?
Annie's song. It's one of the more popular ones.
Okay, I'll check it out.
Being on an airplane is also good.
Okay. All right, man. Look at all the things you know.
Steely Dan's good too. Listen to Steely Dan?
Yeah, a little bit. A little bit. I'm more of an Eric Clapton, Pink Floyd, Led Zeppelin,
That's good.
Jimi Hendrix type, you know.
Talk to Ben about
Adrian was trying to turn me on to country. And you know, we're gonna continue to try to work at that. But what about Led Zeppelin? Greatest band ever?
Ben loves Led Zeppelin.
Ben does?
It's his wallpaper.
Ben does
Really?
love Led Zeppelin, yeah.
Okay.
We listened to it on a trip last summer.
Really?
Yeah.
All right. Well, I think I have a Led Zeppelin CD, some songs that he does not have. I'd like to turn him on to that because there's some really good stuff. Very good. Why are you laughing? There's nothing funny about Led Zeppelin. Led Zeppelin deserves our reverence and attention. Eh? Okay. All right. Thank you. All right. Suppose A is negative and you run it through synthetic division. If you come up with signs that are always alternating, then we know that A is a lower bound. A would be a lower bound. So in this situation, I'm going to take what we believe to be the lower bound. It is the negative 1. Oh, that was horrible. Come on, Gens, get your act together. And I'm going to run it through our synthetic division of 1, 0, negative 3, 2, and negative 5. Drop the 1 and multiply. Give you a second to get caught up there. What do you notice about the signs? They alternate. Therefore, negative 3 is a lower bound. So what that means in context of the problem that we're looking at is if you were to set this up, you would only try numbers that would exist between positive 2 and negative 3. Like that's the only place you would set your sights. I don't use upper lower bounds theorem very much. I use Descartes' rule of signs all the time. And now we're going to see how it takes place. This is what your test will look like, okay? You'll be given a number of problems that look like this. Find all rational zeros of the polynomial. Find irrational zeros as well. Whenever appropriate, use the rational roots theorem, upper and lower bounds theorem, Descartes' rule of signs, quadratic formula, other factoring techniques. And, by the way, make sure that you sketch a graph. Looks like a lot, doesn't it? I will write out what I'm looking for, but this is what I'm looking for. I'm looking for the degree. I'm looking for the number of positive real, the number of negative real, the number of total real solutions. I'm also looking for the rational root choices. I'm looking for the solutions. And finally, I'll be looking for you to produce a graph of your polynomial. If you do not know how to navigate through these problems, you will not do well on the test. On your assignment, you have 2 problems that look like this. Sometimes people will skip them because they're like, oh, those will take a little bit extra time. Those are the most important ones for you to do because that's what your test is going to look like. So let's get started, okay? Degree is 3. How many sign changes do you see? 1 there, 1 there. Everybody good with 2? So I have 2 or 0. There's 2 or 0. Okay? Let's consider the negative one. So I need to look at P of negative x. P of negative x is negative x cubed minus 3x squared be a plus 13x and a plus 15. How many sign changes do you see there? So there is 1 negative real. Guaranteed we're going to have 1 that's negative. I add those together. 2 and 1 make 3. 0 and 1 make 1. So there's 3 or 1. My rational roots, notice on the end here I have a 15. So I have 1, 3, and 5, and 15. And up here I have just the number 1. So my rational root choices are plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. What would you like to try? Evie says so quietly, 1, with a little smile on her face. It's always good to try 1. If it works, we should get 0 for the remainder. So if 1 worked, what's the factor? X minus 1 is the factor. So I have x minus 1 times x squared minus 2x minus 15. That's how it factors. And from there, we can factor to x minus 5 times x plus 3. Notice our solutions are 1, 3, and negative 5. Quick sketch the graph. Are we okay with the graph? Okay. Now watch this. Grant?
X equals negative 5, but then you have it.
Oh, sorry. It should be negative 3 and positive 5. Sorry about that.
Okay.
Now, look at this. Positive 1, right there. Negative 3, right there. Positive 5, right there. You've seen that before. You're not surprised, right? But now look at this. How many of these are negative? One of them, right? Negative 3 is the only one that's negative. How many of these are positive? 2. We found 2 that were positive, 1 that was negative, for a total of 3. Like, that lines up perfectly. Exactly what we predicted. Flip it over. Last one. Oh no, Mr. Getz gave us the 5th power. Is that even possible? I don't think it's possible. What do you think we should do, Alex? We quit?
Quit.
Alex says quit. Last hour said we persevere. We'll take last hour's advice. We have the degree, we have the number of positive real, the number of negative real, the number of total real. We have the rational root choices. And then we have our solutions. And we have our graph. Between you and your peer, please figure out positive real, negative real, and total real right now on your own. Ready, set, go.
Gotta switch there. Gotta switch there. 4 here. 4. So that's gonna be 4 or 2 or 0.
So we need
Yeah, we'll pre-count one for you. Got a killer group in here. Got Alex Palmer.
Interesting.
Check him in to do some mathematics with us today.
Let's go. Do they know like draw those glizzies?
They know you draw the glizzies.
Oh,
They see that their dog can eat your dog.
oh, they're lying.
They don't know how tough your dogs are. Adrian has challenged you to dog wrestle.
All right, have fun.
All right, you have a good one.
Goodbye.
Later.
Is that Connor's back then?
I don't really know. Okay. I got 4 sign changes. Is that what you got?
Yeah.
So 4 or 2 or 0. Okay? If you plug in negative x, you should have a negative x to the 5th minus 3x to the 4th plus x cubed plus 11x squared plus 12x plus 4. So notice in that situation, we end up with just 1 sign change. You have 1 negative real. That means your total real is what? 5 or 3 or 1. Now, Mr. Gans did give you a 5th degree polynomial, but look at the choices. We've got a 4 on the end here. We've got a 1 on the end there. So our choices are obviously just going to be plus or minus 1, plus or minus 2, and plus or minus 4. And there are 6 choices, and yet we only have a 5th degree. So that's pretty good. We got pretty good odds of selecting right, don't we? What would you like to try first? Always start with 1. Okay? Always. Every time. I try 1. Got 1, negative 3, negative 1, 11, negative 12, and 4. Drop the 1, I get 1. Negative 2, negative 2. Negative 3, negative 3. 8, 8. Negative 4, negative 4, 0. Did 1 work? It did. So that means that x minus 1 is a factor. Now, as you're trying to make a guess about what to do again, notice that the number of positive reals, that there's an even number, isn't there? There's no way there could just be 1 positive real. So you got a good shot at trying 1 again. You know what I mean? Like if there was only 1 positive real, then we shouldn't try another one right now. But there's 2 or 4. So let's try to see if 1 works again. I'm going to run 1 through that. See what I get. Get 1, 1, negative 1, negative 1, negative 4, negative 4, 4, 4, and 0. So 1 worked again, so I have another x minus 1. Now, some people just continue to try numbers, but I notice something, and I don't know if anybody else notices this, but I get an x cubed minus x squared minus 4x plus 4. Does that factor? It does. If I can factor at any point, I choose to factor. And in this situation, I can factor by grouping. I'm going to take an x squared out, and I'll be left with x minus 1. And then I will take a negative 4 out, and I'll be left with an x minus 1. Now as I factor out the x minus 1, I get x squared minus 4. So you have a third x minus 1, and then you have an x plus 2 and an x minus 2. So my solutions are 1, 1, 1, 2, and negative 2. What is awesome about that is, again, the number 1 sits right there. The number 2 and negative 2 sit right here. And then as you look up, I have 5 real numbers. I have one of them that's negative. It would be this negative 2. I have 4 of them that are positive. 1, 1, 1, and 2 for a total of 5. It's completely dissected ahead of time. We know how it's going to work. And if I sketch this graph, 1, 2, 1, 2, it's a 5th degree, which means it starts and ends in opposite directions. It's going to go through negative 2, come down through 1 at a triple root, and then back up through positive 2. I can also sketch the graph. That is what the majority of your test is going to look like. That kind of problem. That's what you have to be prepared to do. There are 2 problems on your assignment that are dedicated to that. Make sure you do not skip those. Tomorrow we have an easier lesson and a shorter lesson. Tomorrow we should be able to give you possibly enough time in class tomorrow to be able to finish your assignment in class. That's the goal, okay? To get you some work time tomorrow. So go ahead, get busy on that. Got about 4 minutes, not a lot of time. If you want to work, great. If you're done for the day, then you're done for the day. Pictures kind of cut into it.